Hello, everybody. Happy Thanksgiving. I put out the AI Notes 14 a while ago, but I didn't do a video on them, so I thought I'd do a video on them right now. In the Notes 13, we had an example of a finite state machine. It looked like this on the screen, and you'll notice it had reject states, accept states, and the grammar had those rules. Now, some time ago, I say at least 40 or more years ago, Noam Chomsky, a linguist at MIT, who is actually quite controversial because of other things, defined a hierarchy of languages by looking at the forms of the production rules. Now, he was a linguist, but it's very much part of computer science. In fact, if you're taking theory of computation, I suspect you've already done it. There are 4 types of grammars, and each of these represents a set of languages. Also, each of them represents a machine type. The machines are models of computing devices. They define what can be computed by each language type. So for all grammars, we have a set of non-terminals. Each grammar has a set of them. These are used to generate the language, and they do not appear in the final sentences of the language. The final sentences are called the terminals. In our example above, the S's are non-terminals, and the zeros and the ones are terminals. Just to show you how many rules it can take, I copied here from one of the sources on the web some of the rules for Python. And Python is not anywhere near a natural language difficulty. The starter symbol, there always has to be one. This is where we begin all our derivations. What the object is can we start with the S, the starter, use the rules, the replacement rules, and end up with the string of terminals we have. If we can, we have our object in our language. If we can't, we don't have a language in our language. The production rules are called rewrite rules or production rules. What it says is, if you have the left-hand side, you can replace it with the right-hand side. When I see a line like S is replaced by one S or one, or S goes to one S or goes to one, that bar is the OR. So it's really 2 rules there. Now, for example, just using those 2 rules, I can replace S by one S, then the S by one S, then the S by one S, and then the S by 1. So I can get to the string of 4 ones starting with S. In fact, with this particular language, this particular set of rules, I can get every string of ones that has 1 or more ones in it. Now, what's the distinctive part? The distinctive part is the set of rules. And there are 4 types of rules that we can look at. The first languages are called regular languages. They're the smallest group. They are of a very restricted form. The only thing you can do is take a non-terminal and replace it by one terminal, or a non-terminal by one terminal and one non-terminal. These are called left because I insist the non-terminal be on the right-hand side. I guess I should say the left because I make the terminal on the right-hand side. What we just had is a regular language. These languages can be modeled as finite state automata, That's what I had at the beginning there. They are used to create search patterns in programs. For example, the string in the find first of could be written as a pattern in a regular language. These languages are useful in checking that the syntax of programming language is correct. They are too weak to handle natural languages, far too weak. Now, the second type are called context-free languages. Every regular language is a context-free language, but there are context-free languages that aren't regular. All the production rules must be one non-terminal goes to a string of terminals and non-terminals. We don't care what the string is like. We don't care if the terminals come first or the non-terminals. The distinctive part is that if you see a non-terminal, you can replace it. You don't have to worry about what's on either side of it. That's coming next. So, for example, if I have S equal ESN empty, E equals 0, and N equals 1, look at the languages I can get. I can get 0S1, 00S11, 000S111, and I can get rid of the N. I put a couple of these here. Basically, what this is that you can have all zeros followed by ones, and they have to be the same size, same number. Now, there's some feeling that context-free languages may be enough to parse the languages, natural languages, and there's some feeling it might not be. Context-sensitive languages just say, well, you have to look around the letter, the non-terminal. You have to have a string. You have to have a string of terminals, another string of terminals and non-terminals on either side. And then you can replace the A by any string of terminals or non-terminals. The context matters. You can only replace the non-terminal if it's in the context of what's on the left-hand side. Now, these are more powerful languages, and they're not the most powerful, though. The most powerful are called recursively enumerable languages. And basically, they say anything goes in the rules. We don't have restrictions on them. If it's not in this group, we can't compute it. There are languages we cannot find a grammar for, and therefore we can't get a machine that will execute them. So we basically can't compute what they are aimed at computing. The basic idea of the machine that does this is a very simple machine. It has a program, the CPU, the code. It has a read-write head, and it has an infinite tape. And what it can do is write symbols on the tape and move from one side to the other. And that's it. It reads what is under the read-write head and does one of three things. It may change the symbol, it may move left or right, and it moves to a state which could be the same state. It has been proved that anything we can compute could be modeled by a Turing machine. Now, Turing also showed that some things cannot be solved this way. So this is a limitation on computers. We can't solve everything. There's a limit. But that machine is so simple, you may not think that it could possibly do everything, but it could. It's just it would take a tremendous number of rules to show how it would do some of the fancier stuff, but it can do it if we wanted to push it. So that's what I wanted. The type 3 languages are the smallest, and basically each group is contained in the bigger one. So the type 0s contain everything below them, and the 1s contain everything below them, and the type 2s contain the type 3s, and so on. That's why it's called a hierarchy. This is a basic concept of computer science. The idea of the Turing machine, the automaton, these are just absolute at the core of computer science. So that's it for now. See you later and have a great Thanksgiving. Bye now.